The next type of reaction that we have is exothermic and endothermic reactions. So these reactions are based on energy changes. So if we talk about exothermic reactions, so it's a type of chemical reaction in which products are formed along with the evolution of heat. So if exo is release, endo is definitely absorption. So if we need to take some examples of exothermic reaction, we always try to remember one thing before writing the examples, that reactants are changing into products. So in these type of reaction, we always write plus heat on the right hand side. So we can even write minus heat on the left hand side, right? Like this, we can mention like this also. Reactants minus heat giving us products. This also indicate exothermic reaction. Both are exothermic. So most of the combustion reaction, we discussed combustion reaction. It's a type of oxidation reaction. So most of the combustion reactions are exothermic. So methane burning in the presence of oxygen, giving off carbon dioxide and water vapor. So methane is a gas. This is also called as marsh gas, and methane is also present in marshy areas. That's why the marsh gas has a common name. So carbon dioxide and water vapor, and we can write heat plus heat over here just to indicate that this is exothermic in nature. So we can balance this. So we just have to put 2 in front of water, and this will be perfectly balanced. Then we can write many examples under this. We can write combustion of any kind of carbon based, like carbon reacting with oxygen to give you carbon dioxide. That is also your exothermic reaction. And the one reaction that we did previously, magnesium burning in the presence of air to give dazzling white flame along with magnesium oxide, that is also exothermic in nature. We can even have a reaction of hydrogen sulfide, which is in the gaseous state. It also has a characteristic rotten egg smell. So it reacts with oxygen to give us water and sulfur dioxide. So this is liquid gas. And again, we are going to write plus heat. So we need to balance this. So we can see sulfur. So we have to double the whole reaction. So if we so over here leftover is 3. Okay. So we can have n number of examples for exothermic reaction. Every kind of reaction is definitely either exothermic or endothermic. We can categorize many reactions. So another example that we can take over here is this reaction of lime with water, giving us lime water. This is also very much exothermic in nature. So calcium hydroxide, again we did before, it's called as slake lime or lime water. Calcium oxide is called as quicklime or simply we call it as lime, and it's a perfectly balanced equation. Then we can even write that reaction which is also used in biology. So glucose C6H12O6 in the aqueous state, it's going to react with oxygen to give us carbon dioxide, water, and oxygen, and some heat energy is released. So this reaction is very much used in respiration. So glucose burns in the presence of air that we breathe, gives off carbon dioxide, and the gas which we release out of our mouth, it also has some residual oxygen. So along with water vapor and heat energies, like over here, heat is not released. So better word will be energy. That will be better term. It's a form of heat only. Heat is a form of energy. So we need to balance this. So most of, no, you can say all of them will be 6 if you can see this. Then coming to next part, the endothermic reactions. So how do we define endothermic reactions? So the same sentence, the chemical reaction in which products are formed along with absorption of heat. So over here we are going to write plus heat on the reactant side. So we will be writing like this: reactants plus heat giving us products. Or we can write like this: reactants giving us products, and we can write minus heat on the right hand side. So either way. So coming to examples of endothermic reactions. Now, endothermic reactions, just like I said, most of the combustion reaction are exothermic. It's not always. We do have one exception, so I'll start with the exception only. This reaction, nitrogen reacting with oxygen, so giving us nitric oxide. So I'm going to write plus heat. This is in the gaseous state. So both are gases. So this is our nitric oxide. So we say that this reaction is combustion reaction. This is the only combustion reaction which is endothermic in nature. So when we are studying chemistry, exceptions are always there. So we have this combustion reaction. We need to remember that this is very much endothermic in nature. It's not exothermic, in spite of knowing the fact that most of the combustion reactions are exothermic. So we need to balance this. Then we have many other reactions, including double displacement reactions, including you can say reaction of gases which are endothermic. So let's take this example: hydrogen reacting with iodine, and this is very much reversible, giving us hydrogen iodide in the gaseous state. So you can write minus heat over here. You can write plus heat on the left hand side. It's up to you. Then this reaction, carbon reacting with sulfur. So we are writing sulfur in the simplified form, otherwise the molecule of sulfur is octatomic, having 8 atoms chemically bonded together. Carbon sulfur carbon is in the solid state. So this is also very much endothermic, and it will give us carbon disulfide, which is liquid in state. Then we have this reaction, which is very much important because most of the non-metals. So if we take this red hot coke. Now coke, most of you, if you already know, coke is an amorphous allotrope of carbon. Allotropes are the pure forms of the same element. We have diamond, which is one allotrope of carbon. We have graphite. We have so many. So amorphous is structurally different from the crystalline one that we can discuss in the future classes somewhere. So we have taken this red hot coke. Please do not confuse it with the coke that is available in the market. It's not a drink. It's a powdered form. So this carbon form coke, it reacts with water at a very high temperature, somewhere around 1000 to 1200 degrees Celsius. But right now in this lecture, we are not memorizing the temperatures as of now. So it will give us carbon monoxide and hydrogen gas. So this is actually a form of mixture. So this is endothermic in nature. And the water that I've written, this is in the gaseous state, so it's steam. So we need to give steam over here because most of the non-metals do not react with water. If you have studied about metals and non-metals briefly before in the in your previous classes, so non-metals usually don't react with water, but carbon in the form of red hot coke can react with steam at a very high temperature, and it actually gives us a mixture of carbon monoxide and hydrogen, which we call it as water gas. We even call it as syngas, or we even call it as synthesis gas. So it's a very important reaction, and it's also very much endothermic. Then we go to the next type of reaction, oxidation and reduction reactions. So there are multiple ways to define oxidation and reduction. We don't have only one. So in this lecture, I'm going to discuss only two of them. So we'll start with the basic one. So that's a classical concept, we say. For defining oxidation and reduction reaction. Oxidation is defined as addition of oxygen. We can even say removal of hydrogen, that is oxidation. And we can even say addition of any electronegative atom. So any atom carrying negative charge, it can be a non-metal, or we can even say removal of any electropositive atom. So atom or a molecule. Electropositive means we can say any atom carrying positive charge, it can be a metal also. So we can remember these definitions. Sometimes they are confusing. Oxidation is addition of oxygen, that we can figure it out. Removal of hydrogen, because it's addition of oxygen, so it has to be opposite. It's classical, so it's always going to be oxygen and hydrogen. So we consider this oxygen as electronegative and hydrogen as electropositive. So this electronegative oxygen with the 2 minus charge, hydrogen is with the plus charge. Hydrogen do carry minus charge also, hydride ion, but that we are not discussing in this concept. Why did we write these two definitions? Addition of any electronegative atom or removal of any electropositive atom is also oxidation. Because in most of the chemical reactions, we are not going to get oxygen and hydrogen all the time. We might get some other elements also. So in that case, how we are going to define which, where oxidation is happening, where reduction is happening. So coming to the reduction part, we'll take some examples in couple of minutes. So reduction is opposite of all these terms. Removal of oxygen, because this oxidation is addition. So removal of oxygen, addition of hydrogen. So I'm linking this part, addition of oxygen, removal of oxygen. So removal of hydrogen, so it will be addition of hydrogen. So opposite of what I've written in the oxidation part. Addition of hydrogen. Then removal of any electronegative atom. Then addition of any electropositive atom. So we have done with the definitions. Now time to take the examples. So first we will try to take examples of simple oxidations, and before that we need to remember one thing. When we say redox reaction, so I wrote oxidation and reduction, that is okay, but collectively we call a chemical reaction where oxidation and reduction is happening simultaneously. That is something called as redox. So RED over here stands for reduction, and OX over here stands for oxidation. So reduction and oxidation occurring simultaneously in a chemical reaction. Now, most of the time when we write any kind of oxidation reaction, there is something there is some definitely an element which is getting reduced also. So we can't say that only oxidation is happening. It's always going to be reduction also happening over there. But yes, in certain reactions, our prime focus is the oxidation reaction. That this is oxidation reaction. It's an example of oxidation reaction. But there will be an element always which is also getting reduced. So a simple reaction I'm taking, carbon reacting with oxygen to give us carbon dioxide. In this, we know oxygen is going to be added with carbon. So in this, oxygen is getting added up to carbon. So this is oxidation of what? This is oxidation of carbon happening. So examples of oxidation reactions. So carbon is over here getting oxidized. But what is happening to the oxygen itself? That nobody talks about in the basic examples. So this is reduction. Because if you go back to the definitions, any element adding in over here, carbon is acting positive, electropositive, and oxygen is acting as electronegative. Because carbon is written, you can say, on the left hand side of the chemical formula, if you can see this part. So I told in the previous lectures that any in a chemical formula, anything written on the left hand side is electropositive, on the right hand side is electronegative. That's how we try to understand elements in a chemical formula, that what their behavior might be, because we are not always standing in the lab in order to do some chemistry experiment and figure it out. So this I've written. So over here, carbon is getting oxidized. Carbon is undergoing oxidation. It's adding oxygen. Addition of oxygen is what? That is oxidation. So, and we don't have any hydrogen over here, and oxygen is adding what? Oxygen is adding carbon. Carbon over here is electropositive. Addition of any electropositive atom is reduction. So I've written reduction over here, and this is oxidation. But we are just writing examples of oxidation reaction, but we should never forget this part, that any kind of oxidation reaction, even if you're going to write, it's always going to have something reduction going on. Whether they mention over there or not, reduction will always be there. And in with this example, so let's try to define another thing, something called as oxidizing agent, or we even call it as oxidant. Now we can have a lot of fancy definitions, but we need to remember the simple meaning of this definition, what an oxidant is, what is the oxidizing agent. So I always define like this. So oxidizing agent is a chemical substance which helps in oxidation. That's why the name oxidizing agent. But itself gets reduced. So it's opposite. Since it's an oxidizing agent, it will help in oxidation, but itself it will get reduced. And we call it as oxidant also. So we'll go to the example, and we'll figure it out, what is oxidant over here and what is a reductant over here. Similarly, we have reducing agent or reductant. So you can write this definition on your own. It's going to be very much opposite of what I've written in the first statement. So reducing agent is a chemical substance which help in reduction because it's a reducing agent. Its job is to help in reduction, but itself gets oxidized. So it's opposite. So reducing agent helps in reduction, but itself gets oxidized, and the other name that we have is reductant. Now we'll go to this reaction again. We can explain most of the things with one single reaction. We don't need thousands of chemical reaction to understand a concept. We just need only one. So over here, carbon is undergoing oxidation. So in a simple term, just remember, anything which undergoes oxidation is a reducing agent itself. Anything which undergoes oxidation is a reducing agent itself. Anything which undergoes reduction is an oxidizing agent itself. So opposite. First step in these chemical reactions to figure it out, which element is undergoing oxidation, which element is undergoing reduction. Then the second step is which element is acting as an oxidizing agent or oxidant, and which element is acting as a reducing agent or reductant. It can be element, it can be molecule, it can be compound, anything, that depends. Now, this is a very basic story of redox reactions that we are doing right now. There's a lot of twists and turns that we'll be discussing in the proper chapter of redox reactions. We are doing just very basics as of now. But yes, basics are the roots of chemistry, and chemistry is not a one-day job. Nobody can teach you chemistry in one day. It takes months, sometimes years, and your understanding and your presence of mind also, that how much you want to study this subject. And it's full of mysteries, and it's very fascinating to learn. Next, we are going to take another reaction. Let's take this example: phosphorus reacting with oxygen to give us phosphorus pentoxide. We even can call it as diphosphorus pentoxide, and this is solid in state, oxygen gas, and phosphorus is also solid. So red phosphorus, white phosphorus. So phosphorus is also present in the matchstick head. So phosphorus is, you can say, not that, uh, you can say it's toxic. So let's balance this. We just have to put 2 over here, so then we have to put 5. So 5 into 10 oxygen. So balancing part I've discussed, so I'm just putting the numbers. Figure it out on yourself if you're still not able to understand how I am putting these numbers over here. Like, we are just balancing the number of atoms on both sides. Now in this reaction, let's try to understand. Phosphorus is adding oxygen and it's on the left hand side of the chemical formula. So it's going to be electropositive and oxygen electronegative. Phosphorus is adding oxygen. So addition of oxygen, we know that this is oxidation. And then oxygen is adding phosphorus, which is electropositive. Addition of any electropositive element, that is reduction. So this is going to be reduction and this is oxidation. So anything undergoes oxidation is a reductant itself. So we can write like this: reducing agent, and oxygen over here is the oxidizing agent. Obviously, if one of the reactant is a oxidizing agent, the other will be reducing agent. So if you have figured it out which element, which molecule or compound or element is reducing agent, you can figure it out, the other one is oxidizing agent. And please do remember, we don't have oxidizing agent and reducing agent on the right hand side of the chemical formula. We have everything on the left hand side. Which reactants are undergoing oxidation and reduction? Left hand side of the chemical reaction. What's the oxidant and reductant in the chemical reaction? Left hand side of the chemical reaction. Nothing on the right hand side. Nothing. Right hand side is only helping us understand the change which these reactants are undergoing. Most of the students have come across, they try to figure it out, okay, right hand side something is getting changed. So they might even say P2O5 is a oxidizing agent or a reducing agent. No, that's on the reactant side. So just remember that. Then we can have certain reactions. This is like addition of oxygen, we took example. So what if some removal of hydrogen is happening? That is also oxidation. So removal of hydrogen example, we can take this example. H2S changing into hydrogen. So H2S is gas decomposing. This is decomposition reaction. And sulfur, which is in the solid state. It's a perfectly balanced equation right now. So hydrogen is lost. Hydrogen is, if you see, hydrogen is getting removed from sulfur over here. And sulfur is removing hydrogen. So removal of hydrogen, if you go back to these definitions again, removal of hydrogen is also oxidation. So removal of hydrogen is oxidation. So definitely H2S out of that, because we have a single reactant over here. This single reactant will act as a reducing agent and oxidizing agent both, because we don't have any other reactant. We can't just say we can say that out in H2S gas, in hydrogen sulfide, which element is undergoing oxidation and reduction, that we can define. But if you are going to answer this question, which what is the oxidizing agent and reducing agent in H2S in this chemical reaction, so the answer will be H2S is acting as the oxidant and the reductant both, because we don't have any other reactant over here. So hydrogen is undergoing oxidation and sorry. So sulfur is removing hydrogen. Removal of hydrogen is oxidation. So sulfur is getting oxidized. So this is oxidation. Hydrogen over here is removing sulfur. Sulfur is electronegative element. So removal of any electronegative element is reduction. Here, this is the statement. So hydrogen is removing sulfur. Removal of sulfur is reduction. So we just have to keep these definitions in mind. That will be quite helpful. Then we go to another reaction. So I'm not going to take some complex reactions over here because we can't explain uh, the redox reactions or oxidation reduction with the help of this simple method. There are multiple methods to understand redox reactions. So, one is oxidation number that we will be discussing in the later courses. So, this this reaction H2S reacting with bromine, it's an aqueous solution. It's an aqueous solution chemical reaction giving us HBr, that is again aqueous, and sulfur is in the solid state. So we'll balance this first. Yeah. So now in this, if we need to figure it out which element is undergoing oxidation. So over here, sulfur is removing hydrogen. Removal of hydrogen is oxidation. So now obviously bromine over here is undergoing reduction. That is addition of hydrogen is reduction. So we can say H2S over here is a reducing agent and this is our oxidizing agent bromine. So just remember we can have multiple reactions under this. We can take this example, sodium reacting with hydrogen to give us sodium hydride. We need to balance this. So in this chemical reaction, if you see, hydrogen is getting added up. So sodium over here is adding hydrogen, addition of hydrogen, and over here what is happening to hydrogen over here? Over here hydrogen is getting added up to sodium. Sodium is an electropositive element, so addition of any electropositive element is reduction. So hydrogen molecule is getting reduced over here, whereas sodium is getting oxidized. So this is an example of, you can say, redox. But again, we are never going to categorize all these as okay, this is reduction, this is oxidation. We can just point it out, but we can we can always figure it out that in this chemical reaction, what is undergoing oxidation, what is undergoing reduction, because it's a simultaneous process. It's never going to be one single process. No doubt there is another method to understand it better, and that we are going to do it right now. Next is something I call it as the electronic concept for defining oxidation and reduction reaction. So we define according to this as oxidation, loss of electrons from an atom or ion, Reduction is gain of electrons to an atom or ion. So let's take an example of this. Now this is a typical displacement reaction. Zinc is highly reactive and copper is less reactive. We know that. Now it's a type of displacement reaction, and we can even call it as redox reaction. Most of the reactions are redox. Now if I write this equation like this, zinc reacting with copper ion changing into Zn2 plus ion and copper. So this is the ionic equation over here. So I have removed sulfate radical over here. So sulfate is something called as spectator ions. So we can define spectator ions, ions which do not change in a chemical reaction are called as spectator ions. So over here, if you see clearly, sulfate is unchangeable on both sides. It's not changing into any gas. If you remember from the previous example, like ferrous sulfate, dot 7 molecules of water, green vitriol. So it's decomposing into FeSO4 and 7 molecules of water, which is again decomposing to give us Fe2O3 and sulfur dioxide and sulfur trioxide. In that chemical reaction, sulfate identity is getting changed into sulfur dioxide and trioxide. But over here, sulfate radical is unchanged on both sides of the chemical reaction. That's why we call it as spectator ions. It's a definition. Ions which do not change in a chemical reaction. Their identity doesn't change. So I removed those spectator ions out of this reaction and I wrote, you can say, in this format, in this ionic equation format. And now we are going to understand what do you mean by loss of electrons and gain of electrons. So you can see zinc over here is changing into Zn2 plus ion. So zinc, just remember, any element having no charge anywhere around its atom, no charge over here, so it's carrying zero charge. So the charge carrying by zinc in the elemental state is zero. So whenever, this is loss of electrons, this is definitely loss of electrons. 0 to 2 plus means it has lost 2 electrons. This I have discussed before in the previous lectures also. 2 plus means it has lost 2 electrons. So obviously from the neutral state it has lost 2 electrons. So loss of electron, this is your oxidation reaction. And to be more precise, I am writing half of the full reaction. So this reaction is called as half reaction. To be more precise, we even call it as oxidation half. And how many electrons this zinc is changing, is losing from zinc atom? So it's 2 electrons. Then if we talk about copper 2 plus ions, copper 2 plus ions are gaining the very same lost electron and changing into copper. So again, copper, if you see over here, it's carrying zero charge. So zinc to zinc 2 plus is oxidation, loss of electron, gain of electron 2 plus to 0, that is reduction. So if an atom has gained 2 electrons, so obviously it is getting neutralized. If you see this 2 plus, it had lost, you can say lost state, 2 electrons. It's gaining these 2 electrons lost from zinc, and it is, you can say, getting neutralized. The same lost electron it has gained back. So this is something called as reduction half reaction. Now what do we do of these half reactions? We just add it up. So opposite, just remember one thing, that's why I removed spectator ions. Even if I had added over here, which we should not, but anything same on the both side, anything same on the both side in the sense like this, like on in this reaction it's on the left hand side 2 electrons, same, it should be same number of electrons, and over here on the right hand side again same number of electrons. So these are going to be cancelled off, and we will have this. Anything on the left hand side of this equation will remain left hand side. Anything on the right hand side will remain on the right hand side. No adding up like that. So zinc plus Cu2 plus changing into Zn2 plus and copper. So this is a perfectly balanced equation, and we have even figured it out where oxidation is happening, where reduction is happening, and the same example, the same definition we are going to continue over here. Anything which undergoes oxidation is a reducing agent. Anything which undergoes reduction is an oxidizing agent. That definition is unchangeable. You study oxidation reduction by any method. So it's always going to be this way.